Welcome back to Applied Mathematics. In this video, we're going to be adding rationals. As we have seen with our other operations on rationals, the process here ties directly to the process of adding fractions. When the fractions are like, that is to say they have a common denominator, you can add or subtract across the numerator and then keep whatever denominator you have. So if you have something like 3 over 11 plus 5 over 11, you get 3 plus 5 over 11, which comes out as 8 over 11. The interesting thing about fractions has always been, if you don't have a common denominator, you can often force the issue. For example, in 2/3 minus 1/2. If we take 2/3 and multiply top and bottom by 2, we get 4/6. If we take 1/2 and multiply top and bottom by 3, we get 3/6. And 4/6 minus 3/6 is 1/6. The same thing works with a variable expression. Right? If I have 7 over x plus x over 5, I can multiply top and bottom of the first fraction by 5, and I am going to write it out because when we get to the next couple of examples, it's going to get quite a bit messier. Right? But I can multiply top and bottom of the first fraction by 5. I can multiply top and bottom of the second fraction by x, and I get 35 over 5x plus x squared over 5x, which can be combined and becomes x squared plus 35 all over 5x. All right. Nothing too crazy going on there. It feels a little bit awkward trying to work with variables when you're not accustomed to it, but everything works the same way as what you're always used to. The challenge can be recognizing what the common denominator really is. Right? With working with whole number addition, or whole number fractions addition, if you have some ugly numbers, right, something like 31 over 28, now let's make that subtraction, say minus 17 over 49. There's not an obvious common denominator here because most people are not familiar with the multiples of 28 or the multiples of 49. So a trick that you have certainly learned at some point in the past, although it's probably been quite a while since you've thought about it, is look for the common factors. So 28 factors to 4 times 7, and yeah, we can factor the 4 further, but looking ahead, the 7 is the important thing, because over here we have 49, which factors to 7 times 7. There is a factor of 7 in common between these two denominators. We don't need to worry about that factor of 7 that is in common. We do need to worry about some of the other stuff. There is an extra factor of 7 over here. Okay, we can take care of that by multiplying the 7 into the first fraction, top and bottom. Now that 7 matches up. And then there's the extra 4 over here. We can take care of that by multiplying the extra 4, top and bottom, and then that 4 matches up. And now we have 4 times 7 times 7, or 7 times 7 times 4. The order that you say the multiplication doesn't matter. We have common denominators. Right? Multiplying through. 31 times 7 is 217. 4 times 7 times 7 is 49 times 4, which is going to be 4 shy of 50 times 4, which is 196. 17 times 4 is going to be 68. And now that we have common denominators, we can just subtract across the numerator. 217 minus 68. I really should grab my calculator out, but I don't know where it is at the moment, so I'm going to do this the hard way. Right, 17 minus 8 is 9. 20 minus 6 is 14. And so we end up with 149 over 196. Can that reduce? I don't think so. Right, 196 is 4 times 7 times 7, and 4 itself factors to 2 times 2. So 2 and 7 are the only things we need to check. If I try dividing 2 into 149, I know it's not going to work because 149 is an odd number, and only even numbers are divisible by 2. 7 is a little bit trickier. I might want to go off and try the division. 7 goes into 14 twice evenly. 7 goes into 9 once, but with a remainder. It doesn't work out evenly. There's nothing else I can do. This fraction is not going to reduce. It's just ugly. But I can use the exact same process when I'm looking at expressions involving algebraic functions. So if I have something like 5 over 3x plus, let's say 2 over x squared minus 7x. It is really unclear what we can use as a common denominator between these two rationals. But with a little bit of thought, I might notice, well, 3x is 3 times x. There's not much else I can do with that. X squared minus 7x is x times x minus 7. I've got a common factor of x. I don't need to do anything with that. I've got a factor of x minus 7 over here, which is not in the first fraction. So I'll multiply top and bottom by x minus 7. And now those match up. I've got an extra factor of 3 over here that's not in the second fraction. So I'll multiply top and bottom by 3, and now those match up. I don't technically have to write this next step out. It's just going to be the same thing over again. But I wanted to clean it up a little bit and get a nice version of what's happening before I distribute. Because here's one of those weird quirks. I know that after I distribute, I'm going to combine these, get a single fraction, and the denominator is going to be this common denominator between the two original fractions. Once I do that, my next step is going to be to see if the fraction I end up with can be reduced. In order to do that, I am going to factor the numerator and denominator. Why would I multiply out the denominator only to immediately factor it? I can save myself the effort and leave it in its factored form. In this particular case, that doesn't actually do anything. There is nothing I can do further because 5x minus 29 cannot be factored. On to the next example. This one is really tricky. Because at first glance, 3x to the negative first plus 5x to the negative second does not look like a rational expression. But using properties of exponents, right? X to the negative first is the same thing as 3 over x. And 5x to the negative second is the same thing as 5 over x squared. To get common denominators in this case is not going to be, to get common denominators in this case is not going to be that bad. I just need to multiply this first fraction, top and bottom, by x, so that I get 3x plus 5 all over x squared. This is one of those weird cases. We haven't talked a lot about it, but I'm sure that I've mentioned it in a previous video. The rule of negative exponents is that if you like negative exponents, you are allowed to use them. And 3x to the negative first plus 5x to the negative second is perfectly valid and a simplified form of this expression. But when you're using negative exponents, you are not allowed to use fractions. The other rule is that fractions are perfectly fine. And 3x plus 5 all over x squared is a perfectly valid way of writing this expression. The only problem here is that when you have fractions, you can't have negative exponents. So being able to bounce back and forth between these two expressions is an important skill. Because if you are working with two groups that have different priorities, you have to translate back and forth constantly. I had that experience once in my life. It was not fun. But other than that, there's no real reason that we would have to go through this operation for this expression. You can either write it using negative exponents, or you can write it as a fraction. They are both perfectly valid. The trick of it is that that's not the expression I want to look at. The expression I want to look at is this expression, 3x to the negative first plus 5x to the negative second, all over 1 plus x to the negative first. This expression has negative exponents and a fraction bar, and you're not allowed to have both. You have to choose one or the other. Because there is addition in the denominator, trying to rewrite this expression using only negative exponents is going to be a very painful experience. And for that reason, trying to rewrite this using fractions only is probably the best way to go. So expanding that out, numerator is exactly what we just saw. Denominator, we have another x to the negative first, which is 1 over x. And here's where I have to get a little bit creative, because this 1 does not look like a fraction. But of course, I can take anything and divide it by 1, and it's the same thing, and now it looks like a fraction. Once I have done that, I can find my common denominators. I can rewrite the rational. The numerator is 3x plus 5 all over x squared. The denominator is x plus 1 all over x. It is a fraction that has fractions in it. One of the things that I want to point out here this form of a fraction which has fractions in it is called a compound fraction, or sometimes a complex fraction. And one of the things that you have to pay attention to is, where is the main fraction bar? The main fraction bar is generally a little bit wider than the other fraction bars. When I'm writing it by hand, I make it a lot wider than the other fraction bars to make it really obvious. But sometimes computer software doesn't quite do such a good job, so you have to pay close attention. Right? It is important to find the main fraction bar because that's how we turn this from a compound fraction into something a little bit nicer. Because this is really a division problem. It is 3x plus 5 over x squared divided by x plus 1 over x, which is the same thing as 3x plus 5 over x squared times x over x plus 1. One of these factors of x is going to cancel out, and we are going to be left with 3x plus 5 over x times x plus 1. All right. That was not a simple problem. There's a lot going on in trying to work through that evaluation. And we've had to use every tool at our disposal. Right? We had negative exponents. It's been a while since we talked about those, but we have talked about them. Negative exponents turn into reciprocals. Once we wrote those reciprocals, we suddenly had adding rationals. And we just talked about that. We find a common denominator and we add across the numerator. Then we had a compound fraction or a complex fraction, depending on the language that you prefer. When you have a compound fraction, you can rewrite it as a division problem. When you have a division problem, you can rewrite it as a multiplication problem. When you have a multiplication problem, you can look to reducing the fractions before you multiply everything out, and then you can multiply across. I could have taken one last step here and distributed it in the denominator, but technically speaking, leaving it in that form is just as good, and in some cases is a little bit nicer. So there's no right or wrong between those last two. You should be comfortable writing either option. There is so much that I can do with adding and subtracting rational expressions. There's a lot of weird places that things can go. There's one last example that I want to talk about here, and it's involving the distributive property, where once again there is nothing new in what I'm about to do. And in fact, I'm going to make our lives easy. In this subtraction of rationals, I've already given us common denominators. We don't have to go through and try to figure out how that's going to work. We can just subtract across. Although we do have to be very careful as we do so, because this subtraction gets distributed across all three terms. So we have x squared minus x squared. Those cancel each other out. We're left with 0. We have 2 minus negative 4. And then we have negative 3 minus 4. Right, paying attention to the signs, paying attention to positive and negative here is key. Right, so 2x minus negative 4x is the same thing as 2x plus 4x, which is 6x. Negative 3 minus 4 is minus 7. And this was supposed to reduce from here, which means I copied the problem down wrong because I don't see any mistakes in my algebra. That's okay. We've got our final result. 6x minus 7 over x squared minus 49. Oh, there was my mistake. If you want to have a little bit of fun with this, try putting an extra 2 there. So it's 2x squared plus 2x minus 3 minus x squared minus 4x plus 4 all over x squared minus 49. And then see if you can get that fraction to reduce. That's not an assignment, that's just for fun. But with that, I think I have talked enough about adding and subtracting rationals. I'll wrap up there. As always, thank you for joining me, and I'll see you in the next one.